Good afternoon, dear participants of International Conference APMAS 2020. Well, today I would like to make a presentation, of course, briefly about our research, which will be conducted our group at Institute of Combustion Problems and at ARG Research and Engineering Center. The speaker name, my name is Sanat Tolendiuly. The topic of my presentation is the technology for producing refractory products based metallurgical production waste. On the next slide, you can see a brief introduction about our research. So, metallurgical process produce significant amounts of waste, which can be effect on the environment. In spite of the environmental challenges related to metallurgical waste, the metal extraction industries can be integrated to form a circular economy model that promotes zero waste through the recycling and the reuse of these waste materials. As you know, in modern metallurgical engineering, the formation of solid waste per ton of manufactured products reaches 700 kilograms, where 90% of which is metal-containing waste. Products made from substandard waste of metallurgical production are new type of technical materials that, according to the physical chemical properties, can be classified as refractories. Depending on the purpose, technical condition, temperature, and the reaction parameters of metallurgical aggregates, refractories can be divided in the form of two forms, non-firing and firing products. Non-firing products have many positive properties and they can dramatically improve the quality and efficiency of the repair services of metallurgical enterprises. However, in comparison with firing, their properties is limited to the inconstancy of their technical properties when exposed to high temperatures, melts, and slags. Fired refractories differ significantly from non-fired refractories both in chemical, phase composition, and in the technology of their production. The main aim of our work is to obtain fine refractory materials with properties close to those of first-rate ones in strength, refractoriness, and heat resistance in the number of heat cycles. In two tables, you can see the chemical and the phase composition of the investigated industrial waste and immediate products. These materials contain both refractory and low melting compounds. Refractory with melting points, phosphorate, periclase, decalcium silicate, and the calcium oxide, chromium spinel, aluminium magnesium spinel, calcium aluminates, and the silicon and the calcium oxides promotes the formation of low melting eutectic compounds with a melting point in a wide range from 1200 to 1480 Celsius degree. This is the experimental part of our research. First, the test samples were prepared by a sequential mixing formulation set of samples, moistening and compacting in molds of 40 millimeter diameter at a pressure of 100 megapascal. The technology for manufacturing samples includes mixing coarse grains of the charge with a binder, then rolling the grains with fine powders with a particle size of less than 0.063 millimeter. Then all this material was placed in a die of a mold between two punches and double-sided pressing was carried out to obtain products. The pressed product was dried at 100 Celsius degree during one day and fired at temperatures till 1650 Celsius degree with exposure holding time 2 hours at each predetermined temperature for 3-5 samples. After firing, the products underwent visual control, which consisted in examining their appearance for the presence of large and small cracks, their integrity, and types of destruction during firing, as well as various types of deformations, as loss of cylindrical shape or melting. The samples were carefully sorted. Then, their properties were determined, such properties as ultimate stress in compression, refractoriness, density, and shrinkage. On the slide, you can see short results and a small discussion about this research. The properties obtained after testing for physical and mechanical indicators at 100, 500, 500, 1500, 350, and 1650 Celsius degree are shown in indicated table number 3, from which the change in the refractoriness of products from their composition is visible. The most refractory samples were found to be composition in which magnetic material was introduced. These are a combination of cake magnesit, slag, and magnesit, cake and CSP01, as well as recycling with the addition of chamot and aluminum cement, and a sample of complex composition containing slag, recycling, chamot, and refractory clay. Combination of compositions containing slag, chamot, KCSP, refractory clay, cake aluminum cement, slag, recycling during firing up to 1650 Celsius degree melted and underwent significant temperature deformation. These are samples 33.1, 33.2, and so on. On the slide, you can see the feature number 1. This figure 1 shows the curves change in strength, refractory firing samples at most promising changing their composition and the firing temperatures in the mode of 100 up to 1650 Celsius degree. When plotting curves in the coordinates, firing temperature, and the ultimate stress in compression, promising for the production of samples 17, 172 were identified, contain cake and magnesium. Sample 32 and 1 contain slag and magnesium samples. Samples 34 and 1, 34, 2, 34, 3 contain cake and the CSP01. Sample 41, 2 contains recycling and fire clay. Sample 44, 3 contains slag, recycling, chamot, and refractory clay. By the nature of the curves plotted, it can be seen that the cake and the CSP01 are well combined. However, their strength behavior during firing differs depending on the ratio of the components. If we consider these curves at 4 conditional temperature points, then a decrease in strength is observed, with an increase in the content of charge with cake and in the CSP01 material in the following sequence at 20%, at 40%, and at 46%. Now it's time to conclude our today's presentation. I would like to say that the samples of refractory products based on metallurgical production waste were obtained and studied at various rates of components in a wide temperature range. Their ultimate compressive strength, refractoriness, density, and shrinkage were determined. A graphical representation of the change in the mechanical properties of fired refractories is shown in the coordinates ultimate state in compression and firing temperature. It has been established that the refractory products developed from the waste of metallurgical production in terms of chemical composition, ultimate states in compression, refractoriness approximately correspond to the established standard regulation for forced rate refractoriness. Thank you for your attention.